Hello class, this is Gilberto Fonseca, your TA. Today I will be talking about the conversion of third butyl alcohol to third butyl chloride via the SN1 mechanism. So first, nucleophilic substitution. This is what it entails. You have a substrate, it's an R group with an X, usually a halogen, and then a nucleophile. And your nucleophile is a species like this. Sometimes it's negatively charged. And this is what's going to happen. It's going to be a kind of substitution reaction in which your halogen is your leaving group. So nucleophiles are usually electron-rich species. Therefore, sometimes they're negative. You have R groups. You have amines. You have ethers. You have halogens, ammonia, R and amine, and hydroxide. So two mechanisms of nucleophilic substitution. You have SN2, substitution nucleophilic. That's what the S and the N are for. So you have SN2 and SN1. In SN2, it's a bimolecular reaction, which means that the rate of the reaction is proportional to the substrate and the nucleophile. So rate depends on both substrate and nucleophile. It's a bimolecular reaction. You might remember this from kinetics in general chemistry. In SN1 reactions, the rate of the reaction is proportional to the substrate. So it is independent of the concentration of nucleophile. Therefore, it's an unimolecular reaction. Here are the differences between SN2 and SN1 mechanisms. These are crucial to understand to be successful in the lecture portion of the class and in the laboratory as well. So SN2, what it entails is it's better to have primary substrates. For example, in this experiment, if you were using methanol instead of terbutyl alcohol, this would be an SN2 reaction. Methanol is of course a primary. As you'll see, you would make a primary carbocation if you are doing substitution. SN2, it uses strong nucleophiles, mostly anions. They're necessary. Polar product solvents, you need them so that the reaction takes place. You need a good leaving group so that it all happens simultaneously. And the most important part to understand is the inversion of configuration. Since we call this a reaction that is concerted, as the leaving group is exiting the molecule, the nucleophile, the one that is being attached, is connecting to the substrate. So this has to happen in an inverted way. So the nucleophile is connecting to the molecule from the opposite side of where the leaving group is exiting the molecule, is disconnecting from the molecule. Therefore, you have an inversion of configuration. It goes from R to S and from S to R. There's no carbocation. Right, it's a concerted reaction. So everything happens at the same time, and it all depends on both the concentrations of the substrate and the nucleophile. For SN1, it's better to have tertiary substrates, and it's better to have weak nucleophiles and or neutral molecules. Word of advice: if you're using a secondary substrate, you might use SN2 or SN1. It depends on the specifics. But for SN1, again, you need a protic solvent so that the substrate and nucleophile combo undergo soluble lysis. You need a good leaving group. For both cases, you need a good leaving group. But it's less important for SN1. Actually, no, it's more important for SN1. Sorry, since you usually have tertiary substrates. It's harder for the nucleophile to get in the area that it needs to attack. Therefore, you'll get a racemic mixture. So when the leaving group disconnects from the molecule, you'll have a carbocation. And this is a very reactive carbon molecule in which it's missing, it has a positive charge, and it's missing, it wants the electrons from the nucleophile, and it'll pull the nucleophile towards it as the nucleophile is attacking it. However, this is a three-step reaction. So how does the nucleophile know from what side to attack from? It doesn't, of course. So once the leaving group disconnects, the nucleophile will attack from, if you see the molecule from like a plane like this, like a horizontal plane, it'll either attack from the top or it'll attack from the bottom. Therefore, it'll make a racemic mixture, meaning the compound will have your resulting product will have a mixture of S and R. Now, depending on the specifics of the molecule, it might be a little bit favored towards R or towards S. It depends. So it's a three-step reaction. First, the leaving group disconnects, and then the carbocation is formed, and then the nucleophile attacks. So it's a three-step reaction. So the synthesis that we're conducting today is the example of an SN1 reaction. The OH, we're going to have to do something to it first, and then it'll leave. And then the nucleophile that will form will connect. Actually, no. The hydroxyl, it will do something to it, and it'll leave. And a carbocation will be formed. And then the chlorine ion will be, the chloride ion will connect. The nucleophile will attach, and this is what we're supposed to come up with. The mechanism. In order to be successful in organic chemistry, you have to understand the mechanisms of many reactions. First up is the formation of the oxonium ion. So this electron density will attack a free-floating proton, and it'll create an oxonium ion, which is pretty much, you can see it's water with a plus charge. The formal charge of this entity is +1, as you can see. You get 1 per each bond, 1, 2, 3, plus the 2 electrons here. So that's 5, right? And then the valence number for oxygen is 6. So 6 minus 5, the number of electrons that we just counted, that's +1, right? So that's how you calculate the formal charge while you're writing your mechanisms. It's important to keep track of these, as you have to be able to draw these mechanisms. So after the formation of the oxonium ion, which is pretty fast, you get a formation of the carbocation. This oxonium ion is a good leaving group. It doesn't want to stay here. It wants to go out into the world and become water. So the oxygen will carry these electrons, and it'll become water, H2O, right? And as the oxygen, which is very electronegative, pulls off these electrons, carbon here remains naked. It misses some electrons. There you have the terbutyl carbocation. You have 3 methyl groups and a carbon here. Then it comes the attack of the nucleophile. So maybe you were wondering where this proton comes from. It's actually from the acid, from the hydrochloric acid that we added. It does this naturally. Hydrochloric acid likes doing this, likes dissociating. So as this is happening, the chloride ion is waiting for this to happen, for the carbocation to form. As you can see, it's kind of slow, because still oxygen, like I said, is electronegative. It still has affinity for here to the other electrons. However, this is going to happen naturally as well. So when that happens, the electrons from chlorine are going to attack the naked carbocation. And this happens really quickly. And this can happen from the top, or this can happen from the bottom. But since terbutyl alcohol is not, it doesn't have a chiral center or any symmetry or anything like that. It's just a straight up compound, and it's one kind of compound, right? So you don't have to worry about enantiomers or anything like that. So like I said, the mechanism is SN1. And now solubility. So terbutyl alcohol is a polar compound, and it's soluble in water because of H bonding. Terbutyl chloride is less polar because there's no H bonding, right? It's not a redox reaction. There's no Lewis base acid or nucleophile electrophile. It's a straight up substitution reaction. The rate depends on the oxonium ion concentration, not on the halide ion concentration. So it doesn't matter, or doesn't really matter how much hydrochloric acid you put in there. It mostly depends on this step. It depends on this step. So there's going to be protons, and those protons are going to you're going to protonate this alcohol group, and you're going to make the oxonium ion. That's what it depends. The ease of the alcohol reaction. So for SN1, it's better to have a tertiary because this will facilitate the leaving ability of the oxonium ion. And then the reactivity of halogen acids, it's better for the one that dissociates most readily, and this is iodine. Iodine is a bigger element. It has more electrons, so then this hydrogen will leave more easily. So that's why it's more reactive. Tertiary alcohols react with any of the three acids, even at room temperature. So that's why we're using hydrochloric acid. It's easier to handle too. The chemicals that you'll use: hydrochloric acid, terbutyl alcohol. These are IUPAC names for it. You're going to use 5% sodium bicarbonate, and then you're going to use anhydrous calcium chloride, and you'll see for what. And so these are your tools. Both you have pipettes, there's glass types and there's plastic types. One or the other might be recommended depending on what you're using and depending on the reagents. I usually use these. You can use them for a lot of things. Note that this bulb is usually reused, and then these the pipettes you recycle depending on the reagent, or you throw away and you discard in the glass waste. If you ever use these, you discard them in the blue barrel waste. Again, a blue barrel is usually one where your tools were contaminated, or you have paper towels that some chemicals touched, right? So safety. Everything you do has to be in the hood. Safety gloves, you have to wear them all the time, and safety glasses as well. Concentrated hydrochloric acid can cause serious chemical burns, and it also produces hydrochloric gas naturally, depending on how concentrated it is, which can cause severe respiratory irritation and damage. So you definitely want to avoid inhalation. You don't want to be working in the bench, always be working in the fume hood. So first, you add 15 mL of concentrated hydrochloric acid. You keep track of the volume that you're using. You then add 3.9 grams or 5 milliliters of terbutyl alcohol. Again, you have to keep track of these numbers. The two reagents may not really mix because hydrochloric acid is aqueous, is going to be diluted in the water, and so it's going to form an aqueous layer and an organic layer. You therefore have to mix the reaction. You use a plastic pass-through pipette to mix the reaction. You keep the tip of the pipette under the liquid, and you draw solution into the pipette and squirt back into the test tube. You keep pipetting, and you keep the pipette in the test tube all times. You do this 15-20 minutes. You allow the mixture to settle into two layers. The upper layer will be the terbutyl chloride. If you don't see any upper layer, you have to tell me. That means something not happening right with the with the with the chemicals in each of your layers. So notice you'll already have terbutyl chloride. So this reaction happens quite quickly, right? 15-20 minutes. You should not have terbutyl alcohol anymore, hydroxide. The plastic pass-through pipette can be disposed of, like I said, in the blue waste bin. Then you are going to perform sort of like an extraction. You're going to do a series of washes, as we taught you in the previous one of the previous lectures. But first, you remove the lower aqueous layer with the pass-through pipette because you don't need it. You only want your organic layer. You position the tip of the pipette at the bottom of the test tube, and you carefully withdraw the bottom aqueous layer. Always keeping in mind that there's hydrochloric acid in there. Then you add 3 ml of water, and you wash the organic layer. This is your organic layer with water. So you're doing this because you want to get rid of the hydrochloric acid remaining in the organic layer, and the water is going to do just that. It's going to dissolve the hydrochloric acid remaining in your organic layer is going to dissolve into the water, and then you remove the water with the pipette, and then carefully and slowly you add 5% sodium bicarbonate and you wash. So think about why you're doing this. You should ask me if you have no idea, but I'll give you a hint. Even if you wash with water, there might still be some hydrochloric acid. So think about why you're adding sodium bicarbonate here. You will also think of why you're seeing carbon dioxide here. After you add, you'll see some foaming, and this is carbon dioxide. So that's part of the reason why you add slowly. So again, you're washing and you remove the 5% sodium bicarbonate layer. Again, this is all aqueous with the pipette, and you're left with the organic layer. You then again add at least 3 ml of water and you wash. And again, you want to remove any aqueous stuff that might be remaining in your organic layer. And then you remove water with pipette. But see, there's a problem. If you added so much water, there might still be some water left, even if you removed everything else. There might still be some water in your organic layer. Some pesky little water molecules that are stuck there. So you want to dry. You want to dry with calcium chloride. So you pipette out your organic layer, and you put it in the dry test tube with calcium chloride, and so you're going to have terbutyl chloride and calcium chloride. You then remove the dry liquid, your organic layer, and you put it in a round bottom flask with with which you're going to perform a distillation now. So this is simple short path distillation. You have your heating well, and then you have your round bottom flask with boiling chips or a magnet, and then you have a Kleisen condenser here, and you should have a thermometer just above the round bottom flask to keep track of your temperature at all times. Your compound is gonna distillate here, or you might collect it somewhere else, maybe in a test tube or cold test tube or reflux apparatus. It depends on what you're doing. But you want to collect the fraction, and it's going to be boiling between 49 degrees and 52 degrees Celsius. And your yield, we're gonna see your yield. It depends. So again, this is another diagram for it. You have a round bottom flask with the terbutyl chloride. Don't forget, right? You always want to grease the joints, because otherwise, with all the vapors and the pressure, they might get stuck. So the Kleisen might get stuck to the round bottom flask, and you don't want that. And yeah, this is the thermometer and the thermometer adapter. If necessary, insert a test tube. Right, that's with small quantity of cold water or ice to avoid condensation. Right. So you should be familiar with how to create yields, how to calculate yields. And this is the percent yield, assuming that you got 2 grams. So after you perform distillation and you had your final liquid, and perhaps you weighted that liquid, or you measured the liquid and then you calculated the mass using its density, then you finally got 2 grams of terbutyl chloride. So when I do my reactions in my lab, I usually draw the reaction on the page of the lab notebook, and then below I have a table of the molar weights, the densities, the equivalents that I'm going to use, the masses, and the volumes of each of my reagents. So in this case, you are given the molecular weight of terbutyl chloride. It's here. The molecular weight of the alcohol is here, and the molecular weight of the hydrochloric acid is here, and each of their corresponding densities. And what you always want to do is calculate moles. So you have the volume, and then you multiply it times the density, and then you divide by the molecular weight, and you get your number of moles. You have the volume of HCl, multiply times the density to get the mass, right? And then you divide by the molecular weight to get your number of moles. This is basic general chem stuff. So your theoretical, based on the reaction, you should get 1:1. So for every 0.05 moles of terbutyl, the alcohol, you should get 0.05 moles of the chloride. But assuming you got 2 grams, so you get 2 grams of the chloride, you divide it times the molecular weight of the chloride, and you get this number of moles. So then your percent yield is that which you got in moles divided by the moles that you should have gotten, right? Actually here. Wait, no, sorry. It's 1:1, right? So 0.05, the number of moles that you should expect. So then your percent yield is 43%. And that's it. I hope you learned something new. Please don't forget to do your quiz and email me any questions. Thank you.